Previous video we saw that the waveform of Godunov's method, and also we generalized the concept of either the wave is moving from traveling from left to right or right to left. For example, we talked about Fn I minus 1 half equals to f of qi minus 1 plus p is 1 to n lambda p minus wp I minus 1 by 2. So this was the waveform that we discussed earlier. This can also be written as f of qi minus 1, the flux at qi minus 1 plus a negative, since the lambda, the speed is negative, and wpi minus 1 half can be written as wqi minus 1 by 2. This is equation number 1. Similarly, when we have the flux at I minus 1 half, we want to compute the flux at I minus 1 half. The contribution is coming from at Qi. Then you need to subtract the positive waves, the waveform of positive values, positive waves, Wp I minus 1 by 2. And this can be written as, in one form, we have f of qi plus a plus delta q I minus 1 half. So it all depends where the wave is traveling from. If the wave at I minus 1 half is traveling from left to right, this is qi minus 1, and the flux is qi minus 1, then you need to add the fluxes, of wave traveling from right to left. But if the wave is from right to left, for example f of qi, then in that case you need to subtract the left waveform. That what we are doing over here. We are subtracting in the case when the flux is at qi and the flux is at qi. Okay, and in the a plus and a minus form, it is written over here. So this becomes equation number 2. Now if you subtract equation 1 and 2, subtracting equations 1 and 2, we have, for example, f of qi minus f of qi minus 1, and just subtract that, minus or plus. First of all, it should be plus a plus delta qi minus 1 by 2 minus f of qi minus 1 plus should be minus a minus delta q I minus 1 by 2. So we just subtracted these two equations. And these can be rewritten. On the left hand side, you can also see that we have fn I minus 1 half. This will be equal to 0. So we have f of qi minus f of qi minus 1 by, I'm sorry, qi minus 1 is equal to, and we have, for example, a plus delta qi minus 1 by 2 plus a minus delta q I minus 1 by 2. So that's what we get. You can see that there is delta q I minus 1 half, the same difference, but the coefficient is positive, and delta q I minus 1 half is same in all these two cases, but we have a negative only. And this is the flux at qi and flux at qi minus 1, cell number qi and qi minus 1. So here you can see that this is a flux difference, or we say that flux splitting. Since we split, which we already discussed before, the splitting is based on either the wave is moving from left to right or the wave is moving from right to left. If the wave is moving from left to right, then we have lambda positive. When we have wave moving from right to left, then we have lambda negative. So we need to split the flux as well, which we already did, and we already given a plus sign and minus sign. This plus and minus sign in the superscript shows that the wave is from left to right or right to left. Okay, so we already saw that what is that flux. Okay, now if we write, suppose if we write that the flux should remain conservative, nothing can enter more than what it has. So we have Fn I minus 1 half, that will be equal to f of qi minus a plus delta q I minus 1 half, and this should be equal to f of the flux at qi minus 1 plus a minus delta q I minus 1 by 2. The flux should conservative, so it means that the flux at I minus 1 half cell, I minus 1 half cell should be equal to the flux at f of qi, and the contribution from positive waves which has positive values, and it should give you the same value at I minus 1 half. Otherwise, it will not be conservative. So we can write, for example, uh, we can also write this as, if we just look into the previous, some previous equation. Okay. So we can also write it as Fn I minus 1 half, Fn I minus 1 half is equal to a plus a minus qi minus 1 plus a minus qi minus qi minus 1. Okay, so from here we have, after some cancellation, we have a plus qi minus 1, and this will be cancelled out. Maybe I just give you the details. Plus a minus qi minus 1, a minus qi minus a qi minus 1. This will be cancelled out. Then we have a plus qi minus 1, a minus qi. This we already discussed earlier. Remember that once we had this equation a plus delta q I minus 1 by 2, that was equal to r omega positive, r minus, and qi minus 1. That's what we had earlier. When we put the value, that value into the equation fn I minus 1 by 2, then we have a qi. For this equation is I minus 1 p1 to m lambda p minus wp I minus 1 by 2. When we put that equation, this equation, into this equation, then we get that form over here. So you can simply put a plus delta q I minus 1 half with these values. Maybe I just expand it for you so that it is more manageable and more understandable. The complete equation is a plus delta q I minus 1 half r omega plus r inverse qi minus 1, and that will be equal to r omega plus, that will be equal to alpha I minus 1 half, and we have, for example, in the waveform, in the scalar, in the component form, lambda p plus alpha p I minus 1 half and rp, and we can write it as a plus delta q I minus 1 half. That is where we started the value. Let me just call it 1 so that we can, and actually we want to understand where this is coming from. Then we have, for example, one equation fn I minus 1 half, which actually I have written over here, fn I minus 1 half. I can repeat again, aq I minus 1 plus p is 1 to m lambda p negative wp I minus 1 half. So after some modification, you can see that we have, for example, we have this value. We can put the value of this over here with a plus delta q I minus 1 half. So we can probably get this value over here. from Fn I minus 1. We have Qi minus 1 and A can be written as A plus A minus. Let me just sort out plus, and then we have, for example, A minus, and this is, so we have A plus A minus Q I minus 1 plus, and we have, for example, this is for in matrix form, this can be written as A minus. So we have A minus, then we have WPI minus 1 half. WPI minus 1 half can be written as QI, can be written as QI minus 1. So when we expand that, A plus QI minus 1, A minus QI minus 1, A negative Qi minus A negative Qi minus 1. So that is A plus Qi minus 1, A negative Qi. That's what we have earlier. In the first case, I actually wrote it directly, and then I showed that why this is Fn I minus 1 half is equal to the right hand side. So I hope this is clear to you. Now, what we can further show that how this flux difference works. Suppose we have flux at Qi minus 1, and we have the cell I minus 1 half, and on the right hand side we have cell number I. This is cell number I, Qi, and this is cell number I minus 3 by 2, and the cell number is I minus 1. The flux at Qi minus 1 is actually due to the value of F, the negative flux from I minus 1, and the positive flux that is from right flux. Okay, so there will be flux contribution at Qi minus 1 due to the fluxes from the left side and due to the fluxes from the right side. So we can write Fqi minus 1 is equal to flux at I minus 1 due to the negative wave plus flux at I plus 1, the wave due to the positive one from the right side. Similarly, we can write f of Qi is equal to, at Qi, the flux at I will be due to the negative flux at I plus, then we have positive at I. So it means that Fn I minus 1 half will be equal to Fn I minus 1 half will be equal to, for example, this is I minus 1 half. At I minus 1 half, the flux can enter from the left side, which is I cell, and the flux can enter from the right side, which is cell I plus 1. Okay, I'm sorry. This is I minus 1. Okay, I should repeat this again. At I minus 1 half, the flux can enter from I minus 1, which is I minus 1, and that is from the positive wave, and the flux from negative at cell I. So at Fn I minus 1 half, the contribution is due to the plus sign, due to the negative sign at respective cells. So this becomes flux, positive flux. At I minus 1 half, we have I minus 1 plus, and then we have F negative, and the flux is at I. Okay, so we can arrange the fluctuations. These are called the fluctuations. Delta Q I minus 1 half, delta Q I minus 1 half. These will be equal to F negative, and we have I minus F negative I minus 1. Similarly, we have A plus and delta Q I minus 1 half Fi positive, the flux from positive, minus F positive, and it is coming from the cell number I minus 1. So these two values, a negative delta Q I minus 1 half and a plus, if there is a negative sign, so we get the negative sign, and for I and I minus 1, the cell number I and cell number I minus 1. When we have plus sign, then we have plus over here, and at cell I and I minus 1. Okay, so this is a negative and a positive. So that's how the flux differencing has been done. Let me just give you some examples. Suppose that we have a one point A, this is A, and another point is B. The flux at A is due to the two values, one is 10 and another one is 5. This is a vector quantity, and the flux has some units, kilogram per meter square per second. The same is the case with at point B, where we have a flux, some particular value, that is 8 and 3. This is the complete vector, the flux at A, at point A, and the flux at point B. Okay, so when we take a difference of these two fluxes, and the difference will be the flux at point B and the flux at point A. The flux at point B will be A3, and the flux at point A will be 10.5. The unit is kilogram per meter square per second. That's how the flux is defined. So when we take just a difference, we have minus 2 and minus 2. This is the difference between two values. We did not discuss either the values in these fluxes are positive or negative. So it just shows that the flux is decreasing at some place. This is an example of flux difference scheme. This is an example of flux difference splitting, or simply call it flux differences, where we did not incorporate either the values are negative or positive. In second case, suppose we have flux vector splitting. What does this mean, flux vector splitting? In flux vector splitting, we have some flux. For example, we have F rho u square plus P and rho E. For example, this is just some random flux somewhere. If we say that there is U is greater than 0, so it means that this F will contain some quantity which has a wave, positive wave. So then this becomes rho u square plus p. This is just a random flux, and we have rho e. Since this flux represents a positive wave, we put that into plus. If we have, for example, some other quantity, rho, the same flux, some random flux, just for an example, if we have u is less than 0, then we can write F negative. And here you can see that for positive, we already have the things over here, and this will become 0 since there is no quantity which has negative values. Okay, so this approach is called flux vector splitting, where you decide your fluxes according to the sign of the waves. Now suppose that we have flux difference. This is the example, flux difference. Suppose we have the same flux F, which depends on Q. Q is the vector, rho, rho u square plus P. Then we have rho E, for example, some random value. Suppose we define it like this. The value at Qi will be rho I, so on. If suppose we say that the next flux is Qi plus 1, then we have rho I plus 1, rho I plus 1, Ui plus 1 square plus Pi plus 1, rho I plus 1, Ei plus 1. Suppose we have this flux which has some quantities. If I take a difference, f of Qi plus 1 minus f of Qi without describing either speed is greater than 0 or speed is less than 0, then such flux is called flux differences. So the answer will be delta F is equal to rho I plus 1 minus rho I, and we have rho I plus 1 ui plus 1 square plus pi plus 1 minus rho I ui square minus pi. And then we have rho I plus 1 ei plus 1 minus rho I ei. This is what we have, the flux differences, without looking at the u greater than 0 or u less than 0. Previously, this flux was dependent on u greater than 0 or u less than 0. Such flux is called flux vector splitting, and such difference is called flux difference splitting. Let me just give you one more example so you can understand this concept very easily. Suppose we have a very simple advection equation. Cu is equal to 0. And suppose the flux is f of u is equal to Cu. Now, if you want to write, if you are asked to write, for example, write the flux splitting, question is to write the flux splitting. So the flux vector splitting will be, if you say that, for example, F plus and Cu, where u is greater than 0, and then we have F negative, then we have, for example, if initially we say that not u, probably maybe c, since c is the speed of the wave, c is greater than 0 and u is also greater than 0. Then we have f plus is equal to cu, and when we have u is probably less than 0 and c is greater than 0, then we have F negative is equal to 0. That is the flux vector splitting. Since the F flux is defined as all the waves which has positive speed and all the wave which has negative speed. Since both these cases stands for c greater than 0, all the contribution will be due to the positive flux. So we will solve this problem. This will be 0. I hope you got the point. Thank you for watching.